Hi everyone, thanks for coming. Today we have Luis, who will talk to us about moduli spaces and left-invariant symplectic structures on Lie groups.
Hi. Thank you for the introduction, and thank you also everyone joining, and also Ivan for organizing and taking the time to send over the emails. And so thank you for that. And so yeah, we like to start. So as he said, the title is Modular Space and Left-Invariant Symplectic Structures on Lie groups. Let's see. So this is kind of a summary of what I have of my research, what I have been doing these last years. So the problem can be summarized like this. So if you give me a Lie group, I want to classify all left-invariant symplectic structures, or in any case, obtain some conditions for the existence of left-invariant symplectic structures on that Lie group. So some known results. Let me see. This is. I think this is. Let me put this actually in full screen mode. This way. So yeah, there are interesting results in the structure of symplectic Lie groups, and I always like to clarify that by symplectic Lie group I mean a Lie group that is endowed with a left-invariant symplectic form. So it's not the symplectic Lie group, the symplectic group of transformations that preserves at. Just wait, let me. Okay, this is better. Okay, let me fix my screen here. Like this. Okay, so usually they are called symplectic groups. Just repeating myself, and it's a Lie group that has a left-invariant symplectic form. So there are some classification results, but actually the only complete result is up to dimension 4. There are some other results in 6 dimensions for some particular cases, like the nilpotent case, some special cases of the solvable case, and some other cases in other dimensions, but still the general picture is far from complete. So my main results so far can be summarized in these 2 statements here. So they are about the classification of left-invariant symplectic structure on 2 particular. So the first one is a classification in these 2 particular Lie groups. The second one is a classification of left-invariant symplectic structures in a family of almost abelian Lie groups. So I will explain later a little with more detail what these 2 theorems mean, or the definition of these groups. But before this, I would like to kind of state the setting of the problem and the main strategy to get to those results. So first, the setting. So if we have, I will start with a simply connected. Nothing strange to happen when I go from the Lie algebra to the Lie group to the Lie group. So if G is a simply connected Lie group, this G will of course denote its corresponding Lie algebra, and because I'm interested in symplectic structures, it will be an even dimension Lie group. And then we have these 2 sets, the set of all left-invariant non-degenerate 2 forms on G. And then we have the corresponding set of non-degenerate 2 forms on the Lie algebra. So notice here that I'm still not adding the closed condition. I'm looking for symplectic form, but first I will study these sets only of non-degenerate 2 forms. Still, again, not adding the closed condition for the 2 form. And for the previous 2 sets, well, we know that these 2 sets can be identified. So I can focus on studying these. And if I consider the action of the general linear group given by this on a 2 form omega, then I can also write this space as an homogeneous space, where this SPN is the usual symplectic group of transformation that preserve the canonical 2 form. So, but this space, so I'm interested in this space, but this space is too big, or it's too big and it can be very ugly. So a natural thing to do is to introduce a moduli space. So a natural way of introducing the moduli space is, well, first, very normal definition. We have the automorphism group of the Lie algebra. It's just the maps that kind of preserve the bracket. And then we have here the constant maps without the zero map. So first we have an equivalence relation that define a natural equivalence relation between two forms in the Lie algebra. So we will say that two forms, omega1 and omega2, are symplectomorphically equivalent up to scale if, of course, as we expected, is if we take the pullback and multiply by a constant non-zero, then we get the other one. So a very natural way of defining some equivalence relation between two forms. And then we can also consider the action of this group. So this group here, being as a group of the general linear group, acts over here in a natural way. And this action here, well, gives rises to, of course, the orbit space. So we will denote by this the orbit space of this action over this set. Remember again, this is the set of all non-degenerate two forms on this given Lie algebra. So yeah, this is just the orbit space. I'm repeating myself. We will call it the moduli space of left-invariant non-degenerate two forms. So this orbit space is related to the previous equivalence relation. So we have this rejection between this orbit space and left-invariant non-degenerate two forms here in the Lie group up to symplectomorphism and scale. So the idea of this is that we want to study this orbit space. We want to study this moduli space. And if we have an expression for this moduli space, a nice description of it, or if it's quite small, then we can check which orbits correspond to closed two forms. Of course, closeness is preserved in the orbit. So we just need, again, to, if we have the description for this orbit space, we just have to check each orbit which corresponds to closed two forms. So the first thing to do before actually searching for the closed two forms is to find a nice description of this orbit space. And one way of doing it, is to introduce the idea of a set of representatives. So take the canonical symplectic form on the Lie algebra. So you can imagine this isomorphic to, I don't know, to R to N, and then just taking the canonical basis and taking the canonical symplectic form. And just use the usual this notation for one of the orbits. So the orbit through omega, for example, this will be the notation for the orbit. And a set of representatives. So a subset of the general linear group is called a set of representatives if the orbit space can be described like this. So this element H in U acting over the canonical form gives the whole orbit space. So this might seem a strange definition because actually anything can be, in this sense, you can take, for example, the complete space, and that will be a set of representatives. Of course, so, but the idea is that, of course, even though the set of representatives is by far not unique, in practice, we want the set of representatives to be as small as possible. So or as small as possible, or as nice as possible. So yeah, one way of calculating, one criteria. So the next we have a criteria for a set to be a set of representatives. So if we have here the double coset, where here is here is this group from the left, and here the symplectic group from the right, and then as U is a set of representatives if for every G that belongs to the general linear group, there exists an H in U, such that H belongs to this double coset. So with this criteria, you can see that to obtain a set of representatives, what you have to do in practice is grab an arbitrary element of the general linear group and multiply in a creative way from this side by this group and from this side by this group and try to make it as small as possible. So that's in practice what you want to do to obtain a set of representatives. Again, the idea is to obtain the smallest one or the nicest one that you can. So suppose that we already have the set of representatives is a small or is a nice set of representatives. So what can we do with it next? Well, we can introduce what we will call Milnor type theorems. So first, these Milnor type theorems are called Milnor type because in a famous paper by John Milnor, he was studying kind of like left-invariant Riemannian structures on Lie groups. And inside that paper, when he gives some special case of in the unimodular case and in 3 dimensions. So this is just a screenshot of the paper. He gives kind of a normal form for the brackets in the sense like it didn't matter which metric he took for the unimodular Lie algebra. The brackets could always be described like this, in this normal form with respect to some orthonormal basis. So again, the idea was that it didn't matter which metric he took, the bracket relations had this normal form, and that allowed him to calculate curvatures and other stuff. So inspired by this result, inspired by this result, so we can kind of, using the set of representatives, we can introduce the same kind of theorems in this sense. Well, later I will explain a concrete case so that you can see more concretely what I mean by these definitions. So by Milnor type theorems, in my case, I mean like well, first just to remember, if we have a symplector vector space, a basis is called symplectic. If we respect to the 2 form, we have this. So the usual. So the description of the orbit space that we obtain with a set of representatives gives rise to Milnor type theorem. So what I mean is that for any 2 form, we will give a normal form for the bracket product with respect to a symplectic basis. And the simplest the set of representatives, the simplest this normal form. So again, this will be what I mean by a Milnor type theorem will be a lot more clear when I explain a concrete example. But the idea is that, again, that I can describe for any 2 form, I can describe the brackets in a normal form. So now that we have this kind of Milnor type theorem, the next step is to search for the orbits that are closed. Because until now, I have been just studying, I have just been like referring to the space of non-degenerate 2 forms. But I'm interested in in symplectic structures, so I need to add I need to search for the 2 forms that are closed. And this proposition is just is well known, and it's just how the condition for a 2 form to be closed looks at the Lie algebra level. So if we have a 2 form, the Lie algebra level, and we have the corresponding 2 form in the Lie group, then the 2 form in the Lie group is closed if and only if the 2 form in the Lie algebra has this is equal to 0. So this is well known. Obviously, this expression, obviously, it depends on the brackets and depends on omega. So if the brackets are kind of simple, And because we only have to check this, of course, for a basis. And if we are working in a symplectic basis, then this condition is very easy to check. We just put the brackets here, and everything is with a symplectic basis. So we know how this behaves with respect to the symplectic basis. And then, again, this is very easy to check. So how can you apply this to a concrete example? So let's study one concrete example. So let's consider this group. So this is the Lie group, the product of the Heisenberg Lie group and the abelian Lie group. So we denote this the corresponding Lie algebra of H, and this is the corresponding Lie algebra of the abelian Lie group here. And so then the corresponding Lie algebra is this one. The corresponding Lie algebra of this group is, of course, just the direct sum here. And if we consider this as the span of this basis, then the bracket relations are given by this. So the first thing is, well, what is the automorphism group of this Lie algebra? So it's this one. It's very big, actually. So this is the automorphism group of this. As you see, it's actually pretty big. So big that it didn't fit in this slide. I should have made it smaller. But anyway, it's very big. So this is one of the reasons why first we chose to study this one, because the automorphism group is so big that we expected the orbit space, the moduli space, to be nice or to be very small. So now that we know this, so the first is to have a set of representatives. So here I am talking about the general case, but just because it's easier to write, I will just write for this case, for the 6-dimensional case. But the general case is the same idea. But let's consider the set of representatives for the 6-dimensional case of this example, the 6-dimensional case. So this is a set of representatives. So look what it's saying. This is the canon. So this is the canonical form in this algebra. And then the orbit space can be described by this, where H belongs to this set. And look, this set is very small. It's actually 1, 2, and the parameter here vary between 0 and 1. So it's very small. It has only 5 points. So as we expected, the moduli space is very small, very nice. Well, actually, that this is finite is not surprising because it's kind of already known. Yeah, for example, in this paper, he proved that if we have some kind of parabolic subgroup acting over a symmetric space, then the orbit space is finite. And this is our case because just going back, this is a parabolic subgroup. So this space acting over the space of all non-degenerate forms, that is actually a symmetric space. So it was already known, but still we have this expression. So when we have this expression for the moduli space and this set of representatives, we can give the Milnor frames. So this kind of theorem is what I mean by a Milnor type theorem. So let's see what this is saying. For every two-form, for every non-degenerate two-form here, there is, well, in this case, t is 0, this t is equal to 0, 1, that comes from the parameter here, t is 0, 1. So there is this t on a symplectic basis, such that, you can ignore the k here, it's just a technical detail, but the idea is that we have this symplectic basis with respect to omega, such that the bracket relations are given by this, or by this, or by this. So what I am saying is that for any form, for any two-form, we have a normal form from the brackets in terms of a symplectic base. So what these Milnor type theorems give me is something like, instead of initially you had, just going back to the definition of this Lie algebra, initially you had the Lie algebra given by these brackets. And then you are searching the space of all two forms. So what this Miller type theorem does is that it's kind of, you fix, in some sense, you are fixing this because you are given a symplectic basis, or the two form will always be in some canonical form. But for that, instead of like, the price for that is that the bracket relations change depending on the basis here. But if you get some very nice bracket relations here, then you can easily check which of the orbits correspond to close to two forms. So these brackets corresponds, so these different brackets corresponds to just going back to the different elements in the set of representatives here. So we just have to put this in the formula for checking which orbit is closed. And again, because this is a symplectic basis and the brackets are very simple, it's very easy. And just going back to this, the set of representatives, it happens that this element here for t equal to 0 is the one that corresponds in the orbit space to the only orbit that has a closed two form. So so that is kind of the strategy, the idea is to obtain these kind of Miller type theorems and then search for the orbit that correspond to two forms. So doing this for the general, so doing this for any dimension of this Lie group and also this Lie group has even a bigger automorphism group. So that was the reason that we selected these two Lie groups. So we found this. So this is the first result. This class up to symplectomorphism and scale, there is only one symplectic structure if n is equal to 1 in this Lie group, and there is none if n is bigger than 1. And in this case, there is only one up to symplectomorphism and scale. This is the same in the setting to saying that in the orbit space there is only one orbit that corresponds to a closed two form. I didn't talk about Lagrangian normal subgroups, but the idea here is that again, if we have the Milnor type theorems, because everything is written in terms of a nice symplectic basis, then you can search for some nice subspaces, for example. But I will skip this part. So this is the details of this are in this paper.
Question?
Yes.
So do I get it right that even without the closedness assumption, for both of these groups, the moduli space of just non-degenerate two forms up to rescaling and automorphism is finite? And then when you add the closedness assumptions, it leaves only one point in them.
It leaves, I mean, the orbit. I mean, for example, in this case, if you have 6 orbits in the modular space, you have 6 elements, then there is only one of those orbits that correspond to a closed form. Of course, all the elements in that orbit are closed.
Yeah, sure.
Also up to symplectomorphism. So yeah, it's only one point.
And the same for RH2, I guess. So
yeah, in this it was the same. If n, well, in this case, actually, what you have is if n was equal to 1, it's trivial because any two form will be closed. Yeah. And what you have is that actually in this case, the action is transitive. So you just have like the automorphism group here is even bigger, and the orbit space is only one point. And then you check if that orbit is close or not, and it happens that no. So you have that there is no.
All right, thank you.
So thank you. So these two groups. So again, the reason for choosing these two groups is just that the automorphism group is very big. That was the main reason. But they are also a special kind of Lie group. They are almost abelian Lie groups. So so it seems an almost abelian Lie group is a group such that the corresponding Lie algebra is an almost abelian Lie algebra. So it seems natural to say, okay, what happened with an almost with almost abelian groups and maybe study some cases there. So almost abelian algebras in some sense are like the closest one you can get to an abelian one. So we hope that the automorphism group is also very nice or very big. So let's see. So with some definition, so a non-abelian Lie algebra is called almost abelian if it contains a codimension one abelian subalgebra. So it's almost abelian, not abelian, but it has a codimension one abelian subalgebra. So when you have an almost abelian Lie algebra, actually you can show that it has a codimension one abelian ideal, and that therefore it is isomorphic to this semi-direct product, where E1 is some element in G. So the Lie algebra structure of G is completely determined by this linear map, by the adjoint, by this linear map. This map determines all the Lie algebra structure of an almost abelian Lie algebra. And also in the other direction, for example, so if you have an almost abelian Lie algebra, you have this linear map. If you have a linear map, you actually can define an almost abelian Lie algebra. But of course, different linear maps can define different almost abelian Lie algebras. But still, I do not need to consider all possible maps because we have this result, this known result. So if we have two almost abelian Lie algebras, they are isomorphic if and only if there is a map and a constant such that they are up to similarity. They are the same map. So up to similarity and this constant, they are the same map. So we only have to study. So if I want to study some almost abelian Lie algebras, I just have to consider some nice similarity classes here. And the easiest one that you can think of is the family of almost abelian Lie algebras that you can diagonalize. So we will denote it by this. So this will be, so this is a special family of almost abelian Lie algebras. Again, the abelian Lie algebra that you can diagonalize. And we use this notation. These parameters here is just referring to the parameters in this map here. So maybe we can use the same strategy to this family of almost abelian Lie algebras. And when we use the same idea, that is study the modular space, getting a nice set of representatives, and then checking, getting some Milnor frames, and then checking which orbit correspond to closed to forms, I obtain this, or we obtain this. So the first one is a condition in the parameters for the existence of a symplectic form. So it says that given a two form, again, this is just a condition. So there is a symplectic form in this family of Lie algebras, if and only if there is a permutation such that by pairs, the sum of the parameters are equal to 0. So you have the diagonal, and you have, just going one slide back, this is the map that defines the almost abelian Lie algebra. So by pairs, by pairs, they have to, the sum of these have to be equal to 0. So you always have to have some pairs such that the sum is equal to 0. So again, there exists a permutation such that we have this permutation, and by pairs, the sum is equal to 0. And even more, if we have two forms that are left invariant, they actually are in the same orbit. So that means that they are the same up to symplectomorphism and scale. So if it exists, that is, if this condition is met in the parameters that defines this almost abelian Lie algebra, then it is actually unique. I mean, So I mean, the modular space is not I mean, it's not finite. It can be very big, but if I talk about left, when I check the closed condition, there is only one orbit. There is only one orbit that has that corresponds to a symplectic form. So the proof, I will not write the proof, but the idea is the same. And in this case, the orbit space and the set of representatives is not finite, but it can be described by J triangular matrices. So J triangular matrices is a matrix. If you imagine like a matrix that has 4 blocks, it's a block matrix. If each block is lower triangular or upper triangular, well, that is why a J triangular matrix. The point is that it's a particular family of matrices that behave very nicely with respect to the closed condition, if in this case. So you describe the orbit space by these matrices, and then you obtain Milnor frames, and then you check the closed condition, and then you obtain this result. So I actually did saw this kind of result in this paper, where this is the paper where the 4-dimensional the complete classification of the 4-dimensional case is given. And in some proposition there is this kind of result where if you have omega in this diagonal almost abelian algebra, then she showed that there should be a pair at least, that one pair at least should be equal to 0. So in some sense is an improvement of this result. And so it looks like this, just to the condition looks like this. Suppose that you have these two diagonal almost abelian algebras. So you can see the parameters, and then it's very easy to check. Okay, so this one by pairs. So this with this is 0, and this with this is 0. The other one doesn't matter too much, but at least all except one by pairs are equal to, by pairs, this with this 0, this with this 0. So here there is a left-invariant symplectic form, and is unique. And in this case, if you apply the same condition, there is no pair for this to eliminate with. So yeah, so this has no left-invariant symplectic form. So, so this is the other main result. So the future work, and then the future work continuing the same ideas. Okay, so one is, well, complete the classification for all almost abelian algebras. So remember that abelian algebras, the isomorphism class is up to similarity. So, for example, for doing this, you just have to consider, for example, the map, all the Jordan normal forms, for example, because remember, or the Jordan normal forms, and the calculations will become more complicated, but seems doable. I mean, just seems doable. But more interesting maybe is this, that the modular space is often still too big. So is there some information in the geometry of the orbit space that can be useful for searching for symplectic forms? So I want to talk a little bit about this number 2. And by this number 2, I mean, so I want to distinguish the orbits. So I have the moduli space. So those are distinguished orbit. Those are distinguished left-invariant non-degenerate 2 form corresponds to a distinguished submanifold. So in particular, what I'm asking is, in particular, what happens to the orbits that correspond to symplectic forms? So is there something in the geometry of the orbit space that can help me to search for symplectic form? So a similar kind of question have been studied by Kamaru and other of his students. But instead of symplectic, change every place I mention symplectic, change for Riemannian metric. Every place where I mention left-invariant symplectic, change it for left-invariant Riemannian metrics. And there have been some results. For example, in the 3-dimensional solvable case, the orbit. So for example, in this case, of course, in this case, in the Riemannian case, you are not searching, of course, for closed two forms. You are searching for some nice metrics. For example, if the metric is an algebraic which is soliton, for example. So this result says that if this is an algebraic which is soliton, this is a special kind of metric, if and only if in the orbit space this orbit is minimal. Well, in general, this is not enough, but in the three-dimensional case, this is very nice. So there is some information in the geometry of the orbit space that can help to search for nice metrics.
Sorry, can I ask another question?
Hmm.
What do you mean by minimal? Like, is the orbit space like smooth enough for like a Riemannian manifold?
Yeah, I mean, it's an homogeneity of manifold, so it's the dimension of that manifold, yes. So in this case, of all the possible, this is a minimal. Yeah.
Oh, in terms of dimension, not minimal in terms of dimension. Oh, yeah, yes. I thought in terms of like, you know, like a minimal submanifold of a Riemannian manifold.
I don't know, in terms of dimension, yeah. In terms of dimension. So another result in the similar spirit is that, so if we have G in the algebra, and we have a metric on G, then if this is an isolated orbit, then again, this is an algebraic rich soliton. So it's kind of the same idea. There is some information in the geometry of the space that helps me to find nice metrics. So the idea is if I can do the same for the symplectic case. And the truth is that I don't have any result yet. So of course you can ask something like this, let G be a Lie algebra and this a two form. This is symplectic if and only if this is minimal. I don't think this is true, but maybe at least in some special case. But related to these ideas, something that can be useful and is what I have been thinking lately, how can I use this idea to search for symplectic forms, is the idea of orbit degeneration. So if you have a Lie group action, and again, this is the notation for the orbit, then you will say that an orbit degenerates into another orbit if this orbit is contained in the closure of this orbit. So, and usually it's written like this, but the idea is of degeneration again is that this orbit is contained in the closed, and by closed here is the closure, the topological closure of this orbit. So yeah, degeneration gives rise to a partial order of the orbits. It's also related to the dimension in the sense like if one orbit degenerates into the other, then the dimension is also less. But what happens with the orbit degenerations here in this particular orbit space that I'm considering? Remember, this is in my case is the orbit space of all non-degenerate two forms. So, for example, you can consider the kernel of a two form. So the kernel of a two form is just the dimension. The kernel is just the X is the space. Is a subspace of G such that this is 0. So what I'm saying is that for example, if this omega is symplectic, if and only if the dimension of the kernel is equal to the dimension of G. So this kernel is well defined in the orbits. So of course, it's well defined in the orbits. And then you can show, well, here's not the main result, but it's just a result, is that if one orbit degenerates into another, then the dimension of this kernel cannot be bigger. So with this means that you can you only need to look for the closed orbits, for example, to search for symplectic form. So yeah, this is what I am thinking lately, if this can be useful or not. I mean, one is yeah, grabbing the known results in the Riemannian case and seeing if you can apply it here. And the other is using this idea of orbit degenerations to search for which orbits accept a symplectic form. I mean, look for closed orbits and search there for symplectic forms. Still, I have no result, but maybe it can be used to obtain. But repeating, the idea is, does the geometry of the orbit space have some information that can be useful to find nice two forms, or in this case, to find symplectic two forms. So this is the end. So this is the end. This is the end. These are some kind of the reference. These are a nice summary of all what is known about symplectic Lie groups. These were the classification for the four-dimensional case. And yeah, these papers. Yeah, this is about it. So thank you very much for your attention.
All right, thanks, Luis, for your talk. Does anyone have any questions? Well, I got a couple of those. They're both in the same framework of, so we're looking for left-invariant symplectic structures. And unless the automorphism group of the Lie algebra is huge, it can be a problem because the orbit space can be even up to automorphisms can be big enough. It's just too big for us. So my question was, do you know anything about like considering the case of special left-invariant symplectic form, for example, like Keller forms, or something like? So these are basically two different questions. So I can see obviously two ways in how you can consider nicer left-invariant symplectic forms. One of them is like Keller symplectic forms, and the other is something like bi-invariant symplectic forms. Do you know anything about this? So yeah, it's true. Yeah, of course you can do that. I think there are indeed some results not using this, not necessarily using this framework, but I think there are some results, for example, about classifying color two forms in some particular Lie groups, or also being invariant. There are some non-results, but I still haven't kind of like think about those special cases in the context of this orbit space. So there is no results in the sense of considering the orbit space, but there are results in the sense that yes, there are some people that has considered those, of course, those type of special left-invariant two forms and get some classification results. But in terms of they using some description of this orbit space in this same sense, I don't know. I think no, but. But yeah, if the automorphism group is not big enough, yeah, the orbit space can be very big still. But of course, you don't necessarily need it to be like finite, as long as it has, for example, that in the case in the case that it's just like J triangular matrix, for example, it's still very big. I mean, it's still actually very big. You just have like AC infinity is very big, but the shape is very nice and it behaves very well. So. But yeah, that is another thing I might consider in the future to restrict to some special case. Yeah. Do you know an example of a Lie group with a bi-invariant symplectic structure, not just left-invariant but bi-invariant?
In the top of my mind, no.
Yeah, because it's not clear whether it exists at all, unless I mean maybe something like completely obvious, like abelian case, but
like abelian, yeah, like abelian case. Yeah, I'm not sure. I mean, in particular, to be invariant, I actually haven't thought about the be invariant case. I mean, I know, of course, in the color it does exist. In the be invariant case, I'm not sure. Actually, not sure. The truth is, I'm not sure. But of course, if it's a not trivial case like abelian case, might be, but I'm not sure. That's not sure.
Yeah.